Yeah, if this red light is not on, right, you can remind me. Oh, okay. You saw this red light is not on. Please remind me. Okay, how life, how Max affect your life? What's this? Huh? Onion. Associate as an onion. So you can draw your onion using calculus function. Okay, your onion. Onion, does it look like onion? If not, go back, take one onion, crop, cut it into half. You will see this line. Okay, onion. Using square root and power of even power of x. Okay, give you one choice. You guys want to do exercise first or want to go through one chapter? And this chapter you don't need to pay, how to say? I'll quickly go through this vector function because before we go into vector calculus, but we won't test on this chapter, but we will use stuff from this chapter. So you can just listen as a story. And Buika specifically, not specifically on that chapter, but we'll use things from that chapter. Okay, now. So you want to listen first or you want to do exercise first? Huh? Listen first. Huh? Later you sleepy, then we do exercise. Okay. When you go sleepy, we come back and do integration. Okay. So you can just when I go through this knowledge, you just listen, and then you can ask any question you like. Okay. I think I won't stop. Maybe I'll stop somewhere, but maybe won't. Okay. I'll just quickly go through these prerequisite. Yeah. Because we need it for vector calculus next week. So we'll spend 2 weeks doing the line integral. Okay, what is line integral? Line integral meaning you want to do integration below a line. But last time, your function is drawn on the xy plane, only xy plane. But if we do line integral, we want to draw it in a R3. You can make the line into like a snake in R3. Okay. And then similarly, we do surface integral. Okay, we can do surface integral where the surface is irregular. Okay, in R3. Okay, so we need some notion here. So so far, how many type of function we have seen already? So sequence. So sequence is what? It's a list of number, but we can view it as a function. Okay, function from n to r. I give you one n, you give me one r. A1, A2, A3, A4. Okay, this number live in R. And then we look at series. Series is what? For example, power series, Maclaurin series. Some of you doing project now using this, right? Series what? I input you a number, okay, a real number. You output a number if the series converge. Okay, if the series converge. And parametric curves. Okay, what does parametric curve do? You tell me how the real line sit in, for example, R3 or R2. Okay, how the line sit in R3, R2. You have two variable xy or three variable xyz. Okay, in terms of t, for example, time. Okay, I give you a time. In which second the point stand. Okay, in which second the point stand. And then we learn the functions of multivariables. Okay, function of multivariables that we do double integral, triple integral on fxy, fxy or fxyz, right? Okay, when we do double integral on fxy, what does it mean? We are taking the volume under the surface. And then fxyz, okay, we can do triple integral. Okay, our domain becomes axis, okay, or spherical or cylindrical. Okay, and then last time we said that when we change variable, we need a Jacobian factor there. Okay, Then next, we will deal with multiple n and going from Rn to Rn. Okay, this is what we call a vector field. Okay, whenever you go to physics, okay, they talk about vector fields. In mathematics, it means a function. Okay, function from where to where? From Rn to Rn. I give you a point in R2. You give me a vector in R2. I give you a point in R3. You give me a vector in R3. Okay, every point in this space here, I got a some vector. Correct or not? Like magnetic field, right? How do you make it about magnetic field? If you take two magnets together, you can imagine that they stick together or they repel. So there's like some arrow pulling each other or pushing each other. So at every point on the magnet, you can attach a arrow. Okay, attach a vector. Okay, no? Okay. We will go into detail later, but this one is just some idea introduction. Okay, so we'll quickly go through this chapter here. So we mainly talk about vector function nouns. So we're interested in function from Rn to Rn. So in our case, our n restricted to 3 and below. Okay, R2 to R2 or R3 to R3. So again, in general, a function is what? Is a rule that assigns each element in the domain and an element in a range. So I give you an input, you give me an output. This is the function. Okay. So only one. So the key point here is you give me one, I only can give back you one. Okay, I cannot give back you two. Otherwise, this function is not well defined. Okay. One thing cannot go to multiple things. So a function cannot be a one to many map. Okay, this is prohibited in the definition of function. So then we will consider this vector value function, okay, which we call vector function. Vector value, what is value? Value is what? Number. Okay, value is number. What does this function give you? Okay, the value of this function. So this value of this function is a vector. So so what's this domain? Domain here is a set, maybe it's a set of real numbers, okay, and then the range is a set of vectors. Okay, this is a vector functions. So for example, how do you define this? Okay, how do you define this vector function here? So if I let me see here. So let me write here. So our R here, okay, let's say this vector function is R. Okay, our R, the domain is R, going to let's say R2. Okay, so how to define this function? How to define this function? I give you a time variable. Okay, you need to tell me, for example, 1 second, where do you stand? Okay, you need to tell me X in which coordinate, Y in which coordinate, Z in which coordinate. Maybe you say, I'm at A4. Which floor? Second floor. Right, you need to tell me which height. You cannot just tell me A4. Right, A4 got so many floor, right? Okay, you need to tell me A4. And then which floor? Okay. Make sense or not? So you have, for example, if going to R3, you have 3 variable X, Y, Z here. So each of them is a function of T. Okay. So for example, this RT equals to T square I plus ln 3 minus TJ plus square root TK. Okay. So you just input a value T in, then I'll tell you which position I'm in R3. Okay. Let's see what's the exercise for this one. Okay. So do you know what's the domain for this function or not? Any restriction on T cube? This is a polynomial function. Any restriction on T cube or not? No, right? Polynomial defined everywhere. Square root T cannot be less than 0. Okay, so there is some restriction for the Z direction. Your T must be strictly greater than 0. Okay. How about ln 3 minus t? Ln x must be greater than 0 as well. So meaning x 3 minus t have to be strictly greater than 0. Correct? No? Correct, right? Okay. Then so this means what? T have to be less than 3. So t have to strictly greater than 0. And then strictly greater than 0. And then it is less than 3. Okay, so t, this domain here should be in the open interval from 0 to 3. Okay or not? Does it make sense? Okay. Okay. Wait, let me see. T have to be greater than 0. T have to be less than 3. So what's the issue here?
I thought we can take the value of square root.
Oh, square root 0 allowed. Square root 0 allowed. Okay, so it's a half open and closed. Not open and not closed, but okay, yeah. Closed at 0 and then open at 3. Because square root 0 is allowed. You know? Okay, straightforward. Huh? Okay. And then what's the next thing after we introduce a function? Still remember? No? After we introduce function, what's the next thing we introduce? Last time. What's the next thing we introduce? We want to study the behavior of a function. What kind of behavior? Sorry? Differentiate. Before differentiating, what should we do? How we define differentiation? Still remember? Limit. Okay, so we need to do limit first. Okay, we need to define limit on the vector function. Okay, so how do we do it? We just take limit on each component. That's all. Okay, if we want to take limit on vector function, we just take limit on each component. Okay. So what do we mean by this function converge? So this function is a vector value function, meaning it has to converge to what? To a point or to a vector? Yeah. This function gives you vector. So you have to converge to a vector. Okay. So how do you compare two vectors? How do you say that two vectors is the same? You need to compute the distance. Okay, distance between two vectors. So what's the distance in Rn? Norm. Or you take the, what do you call it? What norm? Is it norm? Sure, theory of slope product. Any name for that? You guys learn any name for that? Norm. Actually, that's called a Euclidean norm. It's in the Euclidean space. Euclidean space are Rn. Okay. So Euclidean norm. Or it's the Pythagoras theorem stuff. Pythagoras theorem. Okay, so you take the norm here. So this is the square root. So how do I put it? Okay, so let me just write it up. So let L equals to L1, L1, L2, and L3 here. So this is a vector. So what's this norm here? So this norm here is just FRT minus L1 squared plus GT. So this one should be a FT in the first component. Second component is GT. And then third component is HT. And then you take the square root. And then this is what we call the Euclidean norm. Okay, because when you go further, norm is a very common notion. There's a definition for norm. So there will be different norm you can define. Okay, there's different norm you can define. And this specific norm is called a Euclidean norm. Okay, so you check this norm After taking limit, it is going to 0. Okay, after taking limit, it's going to 0. So this means your function, okay, when you go to times t, it is really close to the vector L. Okay, make sense? Okay, does it make sense? Okay, yeah, so your vector value, your limit become a vector. Okay, all right, so let's continue. So this one we go through already, right? So if we take limit, then it is equal to taking limit at every component. Okay, so it makes sense that when this RT has a limit, when all the component has the limit, okay, has finite limit. I mean, then after limit, we can discuss continuity. Okay, continuity is the same. If the limit going to A, okay, when the time going to A is the same as the function evaluated at the point A. Okay, then the vector function is continuous. Okay, so you need to check how it behave, how the function behave when you reach A from anywhere, and then your function have to behave the same at that point, exactly that point. So you fill in the hole, or you fill in the limit. Okay, no? Does that make sense? Okay, so you have to remember, always remember this picture. Let's say this part is A, so your function behave like this, at the other side. So the limit is going to this dot here. Okay, then you need to make sure that your function really takes this dot. Okay, only that this function is continuous. If you don't have this dot in your function, then it is not continuous. Okay, there's a hole here. Okay, you need to make sure that your function really takes the value R here. Okay, you fill in this hole here. Then only this function is continuous. Okay, the easiest layman term about continuous is you can draw this curve without lifting your pen. Okay, it's continuous. Okay. So far, any question or not? No? Okay, so far, okay. Okay, so there's some terminology here, okay? Well, let's say we have our XYZ coordinate. We can explain using function ft, gt, ht. Moreover, okay, this h, f, g, h, all of them are continuous. Okay, if all of them are continuous, then this curve you use sketch out is a space curve. Okay, it's a curve in the space. Okay, so space curve. And then all these equation is what we call the parametric equation. Okay, and then these x, y, z are all the parameter. Okay, we have gone through this in the R2 case last time. Okay, if not in R3, we got it. It's the first, not the first. After series, we do this. Okay, parametric equation. So seeing you swap your topic to parametric equation already, or still keep the same? Parametric equation. Send me the new topic. Okay. Tonight, huh? Okay. So here is the space curve in a 3D space. Okay, let's see. So it's something like this. Okay. If you have RT defined by FT, GT, HT, so you can, if they are all continuous, then you trace out a curve in the space here. Okay. Trace out a curve in the space. You can see that this is not an intersection. You can see that this curve go behind. Okay, move behind. Can you see this cross here? It doesn't intersect. It goes behind. It goes behind. Make sense? Okay, I can imagine. Okay. So this is really a vector function here. How should I say here? Just now I say this function give you a vector, right? Every point give you a vector. How I actually get this curve? Huh? How exactly I get this curve here? What exactly happens? Huh? How can you trace this curve using vectors? Yeah, every point, every t, I give you a vector, but how I get this space curve, right? So what are these points on this curve here? They are actually the tips of my vector. Okay, they are actually the tips of my vector here. Make sense or not? Okay, I just join all the tips together. Every point, I have a vector t1, t2, t3, t4, and then I join the tips of my vector. Okay, I can trace out this curve here. Make sense or not? So the picture is something like this. So you r-1, you have a vector, r0, you have a vector, r1, you have a vector, r2, you have a vector, and then you see which position of the tips of your vector, and then join them out. Okay? Okay, make sense? Okay or not? Okay, so maybe let's look at some example here. Okay, if I give you this, can you guess what curve is this? Again, this is very close to linear algebra stuff. If I write in this way, how about I write this way? 1 plus t, 2 plus 5t, minus 1 plus 6t. Is it close to linear algebra stuff or not? Solution to some null space? No way? Like this, eh? No. T is a free variable. No? Yeah. So what is this? I think I talked about this last time. There's one time I talked about this. What's this? T is real. Sorry? What did you trace out with this function here? T is a real line. So what do you get here? Straight line. Okay, you get a straight line. Straight line with what direction? Yeah, which direction? There are two directions here, right? Actually. 1, 5, 6. Okay, you have the direction of 1, 5, 6. But what does the 1, 2 minus 1 do? When t equals 0, this point is on the line. Okay, so this is a line that passes through 1, 2 minus 1 with the direction 1, 5, 6. Right? Because remember, vector, whenever you move to different space, this vector still stay the same. So which vector you are talking about? I'm talking about the vector that start with 1, 2, minus 1. Okay, I fix the vector to one space. And then I take the whole line here. So this is actually a line that passes through 1, 2, minus 1 that parallel to the direction vector 1, 5, 6. Okay. Okay, and you can do some exercise actually. There's some exercise here you can try. I don't want to go through now. But if you met any problem doing this exercise, you can always come back and ask. Okay, you try first. Because this is not the focus of our exam. Although we will use a technique from here. This one is very interesting actually. I thought of this, not thought of this. I think this is a textbook question. Yeah, this is a textbook question here. Okay. The parametric equation is S equals to t cos t, y equals to t, and z equals to t sine t. So what's this shape here? What's this shape here? So s and z, if you square them, they satisfy a circle equation. Okay, but when t increases, the circle that they say increase in radius. Okay, and then in y direction, the t is keep increasing, so it keep moving forward in y. Okay, so what is the shape? So this shape will be this spiraling along the y-axis. Okay, so it keeps satisfying the circle equation, but increasing in radius. Okay, makes sense or not? I think this is very interesting because have you went to a temple before? Temple. Any temple, but there's one temple that has this one temple. There's this one temple that they burn this burn the yeah. Huh?
Is this the incense?
Incense is a yeah what do you call that again? Incense. How to spell? INCENSE, incense. Yeah. Wenxiang is like they Wenxiang is they how's that? Wenxiang is they how do you call it? Stack it? Not stack it. You how to say? Put the minus zero. Too scientific. Or I think compress better. I think compress. Yeah, you compress this downwards, right? This is the incense. But this one you open up. And you open up. Okay, you can think about that. You can think about it. But next time you go to a temple, you will see this. Some of the temple, they'll burn it outside the temple, right? They hang outside, and then this I think it's also called incense in temple, right? Incense, yeah. It's the same thing. Okay. Okay, cool. But there's one interesting about this shape here. Should this shape spiral in this direction or spiral in the other direction? Okay, this really depends on your T. Okay, you should check it out. At least this is what we got last time. You can check whether it's true or not. Okay, so in T equal less than 0 is spiral the other way. And then T greater than 0 is spiral. Well, let me see. This one is clockwise. This one is anti-clockwise. Okay, less than 0 anti-clockwise, greater than 0 clockwise. Okay, can try and check. Okay, good. So this one is about give you a parametric curve. You draw it, or I give you a picture. You give me a parametric function. Okay, this part is about this. Whether you can do this or not, I give you a curve. Can you produce me a parametric equation? Or I give you parametric equation. Can you draw the curve for me? Okay. Yeah. Okay, next. So we have come to this derivative here. Now the derivative here is interesting now. Why? Because my function is vector value now. Okay, my function is now vector value. So you need to take the limit of the difference of two vectors now. Okay. You need to take the difference between two vectors. Does it make sense or not? Take limit between two vectors. Take limit between vectors, what do you get? You get another vector, right? Sure, you get a resultant vector, but tangent is a vector, tangent vector. Yeah. Okay, so you can look at this picture here. You can look at this picture here. So you look at your this curve here, C defined by your RT, right? So let's say you want to find R prime T at P, right? At P here. Okay, how do you find it? Last time, what did we say? You look at all the secant. Look at all the secant here. Okay, look at all the secant. So this secant now is given by this resultant vector here. Okay, R at t plus h minus RT. Okay, this two vector here give you the secant vector here. Okay, and then you see how the secant vector change when you get closer and closer to P. And then this vector R prime T is exactly the tangent vector. Okay. Okay. Seems like more intuitive here. Right. What do we get last time? Last time what we get is just a gradient or just a slope of the tangent line. Okay, but now we really get a tangent vector. Make sense or not? Can or not? Because we really realize the secant vector as a resultant vector of nearby vector. Okay. Okay. Next. But usually we do computation with unit tangent vector. This is very important when we go to vector calculus because one of the integration factor will be unit tangent vector. So usually after you found the tangent vector, you need to divide by the length. Okay, we don't want the unit tangent vector to affect our double integral. It's like what we do in that directional derivative, directional derivative, right? We want the unique direction vector. Okay, we don't want the direction vector to affect our gradient. Our gradient only depend on my function, not depend on my direction. Okay, so we will care a lot about unit tangent vector later. All right, so how to differentiate? Okay, how to differentiate vector value function? Similarly as limit, because you need to know our function limit. I mean, our derivative is defined on limit, but our limit works on every coordinate. So similarly for differentiation, it also works for every coordinate. So meaning if you want to differentiate a vector value function, it is equivalent to differentiate and every component function. Given that your f, g, h are all differentiable, then you can differentiate it. Okay? Or do you want to do one exercise? Maybe do one exercise first. You guys seem a bit sleepy now. Do this exercise. Okay, compute what is r prime t and r prime prime t. Again, given rt here. And then try and find the two vector, the angle between two vectors. Okay, try and do this first. What is r prime t and r prime prime t? So you need to check whether each component is differentiable or not. Okay, if it is differentiable, then you just differentiate. Should be very easy exercise. Okay, after you found r prime t, then try and find what is r prime 0. and r prime 0. And then how to find angle between them? It's linear algebra, this one. So calculus 2 is basically calculus 1 plus linear algebra. For those who send me drafts but haven't get feedback from me yet, do you want to do it after class later? At Zengkang. Are you free or not after class? Not free. Okay. Or eat lunch. Okay. Okay, managed to got it. What is R prime T? What is R prime T? What is, yeah, yeah, and 0, correct. How about R prime T? 2n e power t, okay? And then have you computed R prime 0? 110, 210. Yes, correct. Why actually I disappear my 0 disappear. Correct. Let me see. 110, 0, and 210. Okay, make sure you put this 0 in, although 0 times k is 0. But if you write into a vector form, you make sure you put into the right space. Okay, so what's the angle? You know how to compute the angle or not? Given two vector. Anyone know how to compute a vector using two vector? Does anyone know how to compute angle between two vectors, given vectors? Dot product, right? A dot B equals to what? Length of A times length of B cos theta, right? So I give you A, B already, you can dot them together. I already give you A, so you can compute the length. I already give you B, you can compute the length. So you can take the cos of the fraction, right? What do you get? What's the angle you get? What's the angle you get? In terms of radian, what do you get? Anything? You get 18? I get 0.321. Huh? Oh, you didn't. Yeah, 0.321. Okay, yeah. Sure. 0.3217. Then I should put 2. Right? Okay, okay or not? Okay, we're finding this number. Are we meeting angle this time? Not sure yet. Okay, make sense? Okay, yeah, let's continue. Next. So if you can differentiate a function this way, so what does the differentiation derivative means? So it is exactly the tangent line. Okay, tangent line with that direction at each t. Okay, so it's the tangent line at each t. Okay, maybe do this exercise again. So find the parametric equation for the tangent line to the helix with the parametric equation x equals to 2 cos t, y equals to sine t, and z equals to t at the point 0, 1 parallel to. Okay. So you are given the helix. You're given the helix. Want to find the tangent line at that point. So what should you do? How to find the tangent vector at that point? So just now I told you how to find tangent line, a tangent vector or tangent line at every point, right? So what to do? You differentiate the vector valuing function, okay? And then you evaluate at the point 0, 1, pi over 2. Okay? And then you get a vector. Okay, what does that vector mean? It's the direction of the tangent line. Okay, it's the direction of tangent. And so let's do it. How to find the tangent line? So first, what do you do? So you can differentiate your function ft, right? Okay. So this is the direction vector for who? For tangent line. Okay. This is the direction vector for tangent lines. But we want to find the tangent line at 0, 1, pi over 2. Okay. So at this point, what's the t? At 0, 1, pi over 2, what's the t? The t here. You need to make x equals to 0, y equals to 1, z equals to pi over 2 to find t. Then what's the t? Pi over 2, right? Because z already tells you what is the t. Okay, you don't need to solve the other equation. Okay. Because if you solve the other equation, these two cos and sine are periodic. So periodic will give you multiple t. So which t you want to take? Z already tell you. Just take the pi over 2. Okay. So you need to check at t pi over 2, what's the tangent vector here. So this is the tangent vector. So I tell you a direction of the line. What else do I need? Yeah, how to specify a line? A point and a direction. So I give you a direction already. So which point I need? Right? Which point? What's the point I need? Exactly the 0, 1, pi over 2 point, right? Because tangent line must meet that point. So you can use 0, 1, pi over 2 and this direction vector to make the line. Okay. To make this line here. So this is the line equation. Okay. How to find the parametric equation? You just set s equals to 0 minus 2t, y equals to 1 plus 0t, z equals to power 2 plus 1t. Okay, so this is the parametric equation for the line. Why is this called parametric? Because s, y, z are the parameter. Yeah. Okay. No. And then this parameter only depend on one variable, which is t. Okay, you tell me one period of time, I tell you where's the position. Okay. Yeah. Any question? Any question? Hey, why Roland seems very sleepy? Sleep, you sleep well. I think you also the same last Tuesday. Tuesday you was like this as well. Tuesday. In the Tuesday class. Yeah. Didn't sleep well. Okay. The dark eyes very serious. Yeah. Infected by wasabi. And wasabi didn't sleep, oh. She still didn't get the black eyes. Oh. Become ghost already.
你看还觉得我，因为他这边都可以，然后如果是也好，有 cosplay release 还觉得不好 baby
啊。Okay. Let's take a break. Okay, let's take a break until 2:02. Yeah, the assignment is changed to next Wednesday, and you still can do changes to your assignment. No need to end it so early. Hey, I thought I changed it. I didn't change it. Or I changed the wrong assignment. Maybe I changed the other class one. I remember I changed it a Moodle. Or didn't. No? Maybe I changed the other. Not sure. Okay, I'll go back and check and change it. Okay. But at least I remember I make the announcement in your group chat. Okay, I will change it. 对呀，你不觉得它不对称吗？什么叫不对称？你看这个挂号这么高，这个挂号这么低。哎，这是为什么啊？为什么？因为你没有把它放在前里面，看。Impossible 啊！我是个细致的人。I'll show you。可是事实摆在眼前，要怎么相信？哪里啊？我找一找，在这。诶。我知道，不知道，等下给我看看。为什么你把它变去下面？你为什么把它拉下去？为什么你 subscribe 它？对，这是个问题哦。对，我以为你没有把它放在前里面。对，然后其他都改了。这个是什么意思啊 ？W is in 7 没有，你 W 你通常我们这里会写 W 在这里，the word done W 摆这个，然后就知道 W 是这个答案。然后你说的 PD engine power 是谁的 engine power？ 开 engine power， 然后 time time 是什么？ time 就是 travel time。travel time。travel time 哦。然后 friction between 什么和什么呢？ friction force between car and the floor。对 ，distance 什么呢 ？distance travel 啊 ，distance 去哪里？要这么细致吗？当然了，不能你一个一个写咯，你就 list 成这样咯，不要这样挤在一起哦。你一行，每一个 variable 一行。这也写不完。怎么会写不完？把这个移走啊！这么挤啊，太挤啊！这个 slide。把这些移走。我希望它一样的呀，一目了然。一目了然，大家会看了一样忘记。但是问题是太密集啊。你说的对。对，我这个很简短，大家也看懂的啦。engine power 你不能说是看不懂，就看不懂，看不懂，太看不懂。看不懂，回去真的看不懂，好吧？因为有很多可能性。然后 go unit 是什么意思？就是说能不能给出一些 unit 比较容易点它嘛？或者你这边也有 unit 吗？你到底是用 second 还是什么之类，这样我们才可以配对嘛？但是一个就是我看你写 formula 啊，都没有会在上面标，专门标一个。那他们大家不是默认的就是 second 咯 ，force 默认就是牛顿咯。我们又不是学 physics。大家应该学过的吧？作为一个合格的，没有。写一下比较好，我觉得比较。那我要怎么表示在这里？我在后面加一个逗号，然后写个单位。
OK，
呀，写个单位，这样我们配在一起，就知道这个 formula 会 work 嘛。
OK，
这样都是那一分都讲完呢。
讲得完了，因为很多都是空白，很多不都是那个 menu 啊什么的。
然后这个为什么忽然间我们要找这个东西？你只是告诉我我要这个嘛？
对，我需要知道
对
什么时候最省油，那不就
对呀、
是
你怎么忽然间就扯到我要
就是这里啊？When choosing a car, fuel efficient is also，所以我们想要选这个燃油经济性，就是什么样的车，怎样的车，
那个
最
mu
燃油
跟这个车关什么关系？
因为就是车的跟外表有关系。
你要说啊？
哦，不是 V 里呀，
没有 obvious 不 obvious 的，不 obvious
那这个 V 呢？我觉得 V 就很 obvious 里啦。
啊，会比较 obvious 啊，但是人家会忘记你要提醒的。你跟人家讲了一大堆的 formula，忽然间回来说，哎，
知道我这个是你理解
对
不了我的智慧，
我理解你的智慧，但是
不是
我更理解
我有一个深层的智慧。我犯错这种小错误，别人就会来敲我这种问，我就能解答。他们到时候在 question 他们的时候，他就 Why you here take speed but upper no？ 然后我就
可以，
他们就不会问我太深的问题。
可以。
我要留出点马脚的嘛。
我说写好一点，不然的话不是很清楚在干嘛。人家肯定到这个 slide 就不见了，因为他这里已经要不见了，你要就讲死了，我跟你说你。然后对，然后还有这个就是你为什么没有放 partial？ 你不是
因为没有
there 吗
后面它水是那个大的
啊对
topic 嘛，它水是大的 topic，然后 directional derivative 是小的那个 topic。我这里面主要的是这个东西，就是方向上的 derivative，
为什么是方向上的呢？
就是类似于画一个 x y z 了，不是吗？
对
，x y z，x 就是 speed，y 就是 mu。
对啊，方向上也是这个爬蛇的意思是说往这个方向啊，爬蛇往这个方向。
我当时翻书，它这个是小的那个点，我就想那要不写小的点会不会更加的细致？
没有，爬蛇就是方向啊。
可是我看那个 chapter 11 chapter 2，我看没有，我看看，这里有，我看那个大的标题是这个嘛，但是实际上运用的应该是这一块的知识 directional。
拿进去。
所以按照这个写，按照这个写。
这个是其中，
对啊，其中一点呢。
这个也是用 partial 的那个符号啊。
哦，知道是啊，所以我这里写 directional 还是写。
我知道，但是你刚才写 D 在下面。
OK， 这个我进行了美丽改进。
哦，还有一个我不是很满意的点，就是你的这个 W 啊，到底有几个 variable？ 全部都是 variable 啊，对不对 ？W T F S mu S
variable 是
全部就是全部会变的。
不是啊，
谁不会变？谁不会变？
我怕这个东西写太复杂了。
谁来的？
相不相似啊？
我不认识，不认识。什么？谁全部都会变，是不是？
这个你到时候看成他们的时候问我绝对有备而来。到时候
不，你这个写不清楚，写上去。所以你是全部会变，是不是？没有，你就 W 挂弧 P T F S
P 是不变的吗
？P 是不变吗？你车换了 ，engine 不会换的。
所以这个分两种情况啦，一个是选车的时候，那 P 就会变了；另一个是，
但是你一开始不是跟我讲选车？
是啊，一开始是选车，所以这个我怕要写很复杂，要不然还要分第一题、第二题讨论。
不用啊，不用第一题、第二题，就是这个东西的变量是所有都会变 general， 但是我们只是看哪一个方向变罢了。现在明白吗？
哦，那我就说他在探讨 mu 的时候，
所以你这个有5维哦，你看车的时候有5维耶。
是的，
你从5个方向看你的车。
但实际上，我们如果要选车，肯定是假定就是如果只探讨对
可以啊，
这个 view 的影响，
但是你的
会假定它的 P 是一样的。
但是你的 general formula 是 general 的嘛？然后你要 fix 什么 variable 你就 fix 哦，你明白吗？
那我就在这里。
你的 general， 你的这个 formula 应该是 general 的，只是说我要 fix， 可能说我只看单，
我会自己给他一个 condition 了。OK，
你就 fix 这个 fix 这个 variable，然后看其他方向怎么变，
哦，OK，
对不对？
没问题。好的，我了解了。那我现在去进行一
那 OK 啊，
个，
你整个都会改了吗？还是要我还有画了什么东西
你画的我都改了，后面其
？OK
他的
了，
没了。
然后对，然后你就要解释一下这个 partial 怎么拿出这个东西，这个结构就可以了。
这个 partial 怎么拿出这个
对
结构？
对，结论
哦
结论。
哦，这个我
结论
会讲。
你的 slide 还是太急啊！我告诉你，
我东西
对
太多了，我这个太
你太多不用紧，但是你分散一点，人家还看比较快。你这种全部挤在一起，人家看更慢。
觉得大家会比会
没有，你要把它 structure 出来，就是比如说刚才这个 function，哎，这个东西不是你写一行，然后一整排这个，这样人家比较容易一扫而过，而不会这样一个这样停下，看一下停下，看一下停，它会这样
这个不知道到时交到哪里去啊？交到那个 link 上。
调到 link 上。
那如果我交完以后还想改，比如说我中午
啊
最后进行了完善，
所以我就说不要太早交，等一下我会告诉你们，呀，我慢一点。所以其中一个原因我不要太早放上去，就是等下你们就一直改，好像你们调不了那个，那是我的灵魂，好像是。
OK，那我去改。
先好了，等一下可以吗？OK，等一下上完课可以吗？上完课，你们有离年？不是有1个钟的小时休息？啊，你要知道我是什么老师。数学老有什么东西是数学老师不懂的？OK，开玩笑，OK。
我怎么出一张简单的试卷？
对啊，那个懂但是不想做。我觉得你很成功。我的任务 OK， 来，let's continue。要做 integration 的 exercise 吗？还是继续先 OK，continue finish first 来 OK。So how to integrate if you have different function? Okay, not a single function. Maybe you want to integrate sum of function or sum of vector function or scalar times a vector function or product of function. Okay, product of function got two types here, not just two types, three types. Okay, one type is a normal function. Okay, multiplied by the vector value function. Okay, ft times ut. You can see that this u is both, this f is on both. So this ft here is what? Is a normal differentiable real value function. So it's a function from R to R. Real value function only. Okay. The input is real, output is also real. Okay, it's like you can imagine as a changing constant here. Okay, it changes with time, this constant. Okay, ft. And a two vector function, right? The output is vector. What can you do? You can take dot product. Okay, you can take dot product between vectors. Also, you can take cross product between vectors. And then you can take, what's this? Composite. Okay, composite. Change of variable. Okay. You can think of it as a time change, parameterizing your time. Okay, ft. You change your t variable. Maybe 2t, 3t, t minus 3. Like that. So when you differentiate these functions, what do you do? Okay. So first two here says that actually your differentiation operator is linear. Okay, you can differentiate. You can split the sum and differentiate. Or you can bring out the constant and differentiate. Okay, the bottom four is a bit tricky here. So part 3 is exactly like the chain rule. It's like the chain rule. Okay. Actually, 4 also like a chain rule. Okay. Product also act like a chain rule if you differentiate cross product. Okay, so all these product you can see use the chain rule. Yeah, you can get not chain rule, the product rule. Sorry, product rule. Okay, it's like the product rule. So product rule is what? D differentiate UV equals to U prime V plus V prime U. Okay. So the part 6 is the chain rule. Okay, part 6 is the chain rule. So you because you are in the maths class, right? You should learn how to prove this. Okay, you should learn how to prove this. And prove all these 6 statements here. To use should be easy, right? You just apply this formula. Okay, but you need to learn how to prove them. Okay, how to prove them. So for example, let me show you. So let's say we want to show how to differentiate a constant times a vector value function. So you need to write down your vector value function first, okay, in the vector form. And then how to differentiate the vector value function here. Okay, you just differentiate every coordinate. Okay, so you bring in the derivative. Okay. And then inside here, you can see that you are differentiating a real value function. But linear operator is linear, okay, with the real value function. So you can bring the scalar up again. Okay, and then you can bring all the way out. And then you will get the result that you have the constant multiplied by the derivative of the vector function u. Okay, so you can bring the c out. The derivative. Okay, there's one very interesting application here. So let's look at this. We will try and learn this. Show that if the length, okay, of your image is a constant, okay, then the derivative, okay, or the tangent vector is always perpendicular to your curve. Okay, so if your vector function is always constant, okay, so meaning your point is always constant from the origin. Is it from the origin? Is it necessary from the origin? Yes, right, it is necessary from the origin because you are taking the length of this vector here. And then you prove that r prime t is always perpendicular to rt. How on earth we're going to prove this? How can you deduce length? Okay, how can you deduce an angle from the length? Okay, can you imagine what's the object? Is this what object is this? The vector is always having a constant length. Circle. What's the tangent vector on the circle? Huh? Yeah, tangent vector on the circle. So you pick a point. How to draw a tangent? Huh? 垂直半径 is what? Perpendicular radius? Perpendicular radius. What does that mean? So you can see that this tangent vector here, right, is perpendicular to the vector of the point. Okay, it is true whenever you pick any point here. You see? Okay, but one very key important result here is this R. I didn't fix in R2 only, all dimension, meaning all the sphere. Higher dimensional sphere also works. Okay, not hypersphere. What's hypersphere? Not hypersphere. There's nothing about nothing called hypersphere. Right? Hypersurface got but not hypersphere, I think. Higher dimensional sphere also works. Okay, a ball. You find a tangent. Okay, it's always perpendicular to the vector represent the point. Okay, how to prove this? How to prove this? What's the definition of a norm here? Yeah, what's the definition? Square root of sum of square of component. But what is that? Yes, it's a dot product. Okay, inner product. Okay, dot product. So the length of RT is just RT dot RT square root of it. So instead of square root the dot product, I square the C. All right, so what's next? What can we do next? We need derivative, right? Okay, so we can differentiate. We can differentiate this equation here. Okay, so I differentiate the dot product of two vector value product. What should I get? I use the product rule. Okay, I use the product rule. So I'll get R prime T dot RT plus RT times R prime T. But the right hand side is just a constant. I'll get 0. Okay. So what do I get? I get 2 times R prime T dot R equal to 0. Which means R prime T dot R is 0. Okay, so they are perpendicular. Okay, now dot product. If two vectors dot together, you get 0, then they are perpendicular. Okay. Okay, so this is a very good result in differential geometry. Very easy proof, right? Okay, next, after differentiation, we will do integration. Okay, we also define as a limit. But similarly, what do? We just integrate every component if we want to integrate the vector value function. Let's see, let's see if we have something to do here. Maybe we want to do some exercise. Maybe this is useful later. So let's do this exercise. So integrate this vector function here. Okay. So after integration, what kind of object you will get? Do you get a value or you get a vector? For the description just now, you need to integrate every component. So after integration, after integrating a vector value function, do you get a number or you get a vector? You get a vector. Okay, you should get a vector. See what vector you get for this example. Hello. Okay. Anyone finish? What's the first coordinate you get? 5/6. Good. Second coordinate? What do you get? Wait, let's check. Minus 1 minus E over E. Like this. You got an extra minus than me. Should it be minus 1 plus E or minus E? What the others get? Minus minus plus, right? Yeah. So minus 1 plus E over E. Okay? Minus minus plus. Okay, now, does everyone got this? Has everyone got this for the second coordinate? Third coordinate? Understood. Okay? Everyone should get the same. Okay. Okay, let's continue. So similarly, last time we have touched about length of curve. Okay. Or we call the arc length. Okay. So what's the length of the arc that you draw? Okay. Or the plane curve, or the space curve, or the curve. Okay, we have it now. So this is just the integration of square root of the square of the sum. Oh, sorry. Square root of the sum of square of derivative. The derivative. So we have learned the dot product notation. So what is it? So it is just the Euclidean norm of R prime t. Okay. So the long square root thingy is just the dot product between R prime t. Okay. Let's check this on. How about let's check this on circle? Okay, let's check this on circle. Let's do this on circle. What's the length of a circle with radius 1? What's the length of circles with radius 1? 2 pi, right? Okay, so let's verify this. So let's look at RT, okay, with cos t, comma sin t. And this t is going from 0 to 2 pi. Okay, so this will trace out the base curve or plane curve, the unique circle. This is the unique circle. Okay, so what do we do just now? How do we compute this? This computation is important because in the vector calculus, you also will do the similar computation here. So how to compute this length here, length of this circle here? So we evaluate from 0 to 2 pi. Okay. And then instead of using the square root definition, what do? We use the definition of the norm of my tangent vector. dt. Okay. Okay, no? Okay. Yeah. So now it's easier. Okay, I don't need to go and do these what? Write down all the square root thingy. So what do? I just take dot product of two vectors instead. Okay. So what is R prime t in this case? R prime t is sin t cosine t. Good. Okay, so I dot these two vectors together. You can write it as a column vector or row vector, okay, as you like. Because I'm more algebra, I like this. Okay. So what is this value here? So here we get sine square t plus cos square t. Okay, and then taking square root t. Okay. But sine square t plus cos sine t is just 1. Square root 1 is still 1. So integrate 1 from 0 to 2 pi, you get 2 pi. Okay. Make sense? Okay, good. Okay, see, what's the next thing? Have you guys learned arc length reparametrization or not? Have you guys ever learned that? Arc length reparametrization? No? No? No. Okay, let's see. There's another exercise about the length of helix you can try. You see here. Okay. So although I don't want to compute this result here, I want to discuss the result of this example. Okay, you see this example here. See this example. This is a space curve, right? But you see, where's the endpoint and starting point? It's just the endpoint is just slightly above the starting point. So we start from 100, okay, end at 102 pi. If I move this endpoint down, right, shouldn't I get a circle? Circle. I put this endpoint, project the endpoint down. Shouldn't I get a circle? I should get a circle, right? And then you see, from the 0 to this 110 is length 1. I somehow might get radius 1 circle. But just now we computed what? Radius 1 circle has length 2 pi, but this one 2 pi square root 2. This one is larger, longer, or 2 pi is longer? This is longer. It becomes longer. Why? It becomes longer. Makes sense or not? Huh? Makes sense or not? Maybe yes. Why does it make sense? Uh-huh. Oh, okay. Okay. Uh-huh. Okay. So it's like if you go back and try, okay, you take a circle and then you cut it. And then you move the other end up. You won't come back to exactly top of the starting point because you are not long enough. So to be able to do this, you need to take a rubber that is stretchable so that you can stretch it to the top of the starting point. Okay, otherwise you cannot stay up directly above the starting point. Sense? Okay, because when you travel in height, it takes some length. Okay, yeah. Okay, tomorrow, please don't, please answer in English, no Mandarin. Okay, no Mandarin. Mandarin, I will cut mark definitely. Okay, this one there's no argument there. Right, because tomorrow is an English presentation. Okay. Okay. Okay, you must answer in English tomorrow. Okay, so this is a practice. Okay. Okay, so you can compute the length up to some t. Okay, so this is the arc length function here, we call st. Okay, what's st here? We compute from the starting point a up to some t. Okay, this is the arc length formula. Why do we need this arc length formula? If we differentiate this function here, what I get is just the length of my tangent vector. Okay, so the derivative of this function is my length of my tangent vector here. Okay, what do we do with this? Okay, this one we can do with what is the use of this? Okay, we can use this to parameterize our helix. Okay, we can parameterize our helix here. So just now you see that if I use this helix formula, I get something longer than 2 pi. Okay, I can somehow adjust the time variable here. I'm not using t anymore. Then I can get back my length with 2 pi. Okay, well, what do I do? What do I do here? So first of all, I study what's the length of tangent vector at every point. Okay, I study the length of tangent vector at every point, and then what? Then we can find the relation between time and the arc length function here. Okay, we can find the time with the arc length function here. So what does this mean here? So whenever you increase in time, okay, your length is increased by square root 2 times the factor of your t. Okay. So what? So if I sub my t to be x over square root 2, okay, then I will reduce my increase by the factor of 1 over square root 2. Okay, I claim that this will give you the how to say, this is what we call the arc length reparameterization. So how should I put this? So after you do this change of variable here, you can check that the change of your new arc length function here should be equal to 1. Does it make sense? So we normalize the length of our length of tangent vector. Do you believe or not? Maybe you don't believe. Let me compute for you. So you see, after I do this change, right? Let me compute this r prime, new r prime here. Okay, let's compute new r prime here. R prime tx. Okay, let's compute this r prime. Okay, what do I get? Let's compute this new r prime tx here. What do I get? 1 over square root 2 minus sine of x over square root 2, and then again 1 over square root 2 cos s over square root 2. Okay, and then comma 1 over square root 2. What's the length of this? Length of this. Jinsen, what's the length of this? The length of this? Okay, let's compute this dot product first. What's the first term? Over 2 sine square s over square root 2 plus 1 over 2 cos square s over square root 2 plus 1 over 2. Altogether, you get 1. Square root of 1, you get 1. Okay, so you can see that the new parametric new vector function here have unique tangent vector at every point. Make sense or not? Okay. Okay. Make sense or not? This is what we call the arc length reparameterization. So if we do this, what happened? If we do this, what happened to my curve just now? I get back the length of my unit circle, 2 pi. Meaning what? Meaning what have I done? What have I done actually? What have I done? I divide my time with square root 2. So I somehow slow down my time. I slow down my time.
Or did you actually?
Yeah. Reverse it back to. I don't should. I'm sorry. Huh? Sorry, I didn't slow down my time, but I speed up my time because when I input t equals to 1, for example, it becomes 1 over square root 2. Fair enough. Let's come back here. Okay, so where's my x? My x is going from 0 to 2 pi, right? My x is going from 0 to 2 pi. Let me draw something here. So we got a 0 to 2 pi, my x. Okay. Now what's the value I put in here? Square root over 2. Where's square root over 2? So what have I did here? Should I increase time span? Let me think. Decrease time span. Do I need to change my variable? I think I need to change my. Let me see. Am I right to integrate from 0 to 2 pi again? So where's the previous variable here? So this one is from t going from 0 to 2 pi here, right? What did I do here? So what am I doing here? What am I doing here? So if I change, so my t is going from 0 to 2 pi. If I do the change of variable, this means my new x should be going from 0 to 2 pi over square root 2 to draw the helix. Correct? Let me think. Oh, times, sorry, times, correct. You are correct. So square root 2 times 2 pi. Okay, so my time become longer, right? Square root 2 is 1.4 something. Is it 1.4 something? 1.3 something? Yeah, 1.4 something. So meaning, just now I just take 0 to 2 pi to reach the helix, right? Now I take a longer time to reach the helix. Okay. Yeah, so that's mean I make the time slower. Correct. Okay, I make the time slower. You need to take longer times to reach the whole helix now. Okay. So that means what? So okay, let me draw it here. Okay, let's draw what am I doing? Draw what am I doing? Okay, so just now we have a helix like this going up, right? Okay, and then we need to take t naught equals to 0, and then t1 equals to 2 pi. Okay, but after the change of variable, what do? We still draw the same helix, but I take more times now. Okay, my t0 is still 0, but my t1 now becomes square root 2 of 2 pi. Make sense or not? Does it make sense? Okay, so when I do this computation here, I integrate from 0 to 2 pi means what? I did not take the whole helix. What I do is exactly what I said just now. I take the unstretchable unique circle. Okay, I take the unstretchable unique circle. Okay, I project this helix down here. So maybe I get something like this, right? And then I cut it here. I cut it at the point 110 here. And then I try and trace my helix again. Then I only reach somewhere here maybe. Okay, length of 2 pi. Length of 2 pi. Length pi. Because if you want to fill the whole helix, you need to go to square root 2 over 2 pi. Make sense or not? Okay, so the leftover here is what? The leftover here is exactly square root 2 times 2 pi minus 2 pi. Okay. Can follow? Okay. Yeah. For question or not? This is just about upland reparameterization. I think we won't use it also in the next chapter, but I think it's quite important for you for future. You go pure maths. Okay. Next. So this one I think is some project of some of you. Okay. This is a motion in space. So why are we differentiating the vector function? Okay. So if you differentiate once, it represents what? It represents the velocity. Okay. So you can think of a vector value function as a displacement function. Okay. And then you differentiate, you get the velocity in times in space. And then if you differentiate twice, you get acceleration. Okay. One variable case is like that. Displacement, differentiate once, you get velocity. Differentiate again, you get acceleration. Okay, so this is one variable. Then now we deal with multi-variable. Okay, so you get speed, get velocity, right? How to get speed from velocity? What is the difference between speed and velocity? Sorry? Huh? Integration, no? Velocity and speed is almost the same, right? What's the difference? It's like the difference between distance and displacement. What's the difference? One is scalar, one is a vector. So it means what? Vector has direction. Okay. So speed, don't know about the direction. So how to get speed from velocity? You need to take the absolute value, okay, or take the norm now. Okay, take the norm. Okay. So absolute value works for real number, right? So you also can see the absolute value as a norm, right? Correct or not? What's the norm there? Is the distance between the number with the origin. What is absolute value? Absolute of -2 is 2. Absolute of 2 is 2. Correct or not? You're not just throwing away the minus sign, but you are exactly finding the distance between the number and the origin. Okay, it's the same. When you go to higher dimensional, you also check the distance between the origin and the vector. Okay, so maybe we can just quickly run through this. We have this position vector here moving with RT equals to T cubed I plus T squared J. How to find the velocity, speed, and acceleration? So you just find the derivative of this function here. And then to find the speed, you just find the absolute value of R prime T or the norm of this R prime T here. And then you can see that. Can you see the difference or not? Velocity here is a vector, but speed here is a scalar. Okay, so it really doesn't remember the vector, the magnitude. Okay. Yeah, direction, sorry, direction. Acceleration here, okay, you differentiate twice. You also have direction. Okay, if you want to evaluate at some time t, you just differentiate, just substituting. How many of you doing this kind of project? Chen is one of them, right? Who are? And then Seng, just two of you. Then maybe I need to rearrange you with him. Put you two together. Who is before you, Anna? Who is before you now? After you, Yeah. Same topic put together, easier to listen. Who is before you now? And after you? Or maybe Chen Jack. Who is before you? Or after is log out? Before? Make sure you know who is in front of you, who is behind you, because you need to get ready and then. Then I need to move you then. And Zhongyi, Yixing. Okay, Yixing is a double integral. Okay. Okay. Continue. Let's continue. So this one is the same. And then there's a question about this central Peter force stuff. Okay. Where you differentiate different vector value function. Okay, you differentiate different vector value function. Skip this. Yeah, if you are interested, you can do this, but not too important, this question here. But this question is actually interesting, this one, projectile. Sure. This question is actually interesting. So a projectile is shot from the origin at an angle alpha from the positive x-axis with an initial velocity v0, assuming that air resistance is negligible, and the only external force is due to gravity. So if you throw something up, okay, it will fall down. But how it falls? So you need to find the position function RT of the projectile. Okay, so you need to prove that it falls in this way. Okay, you need to prove that it falls in this way. You need to find this function. And what's the value of alpha? Maximize the range. Hey, this one is very important, eh? Hey, for those of you who play sport, which direction is the furthest you can throw? Which angle? How do you know? Because, huh? Super? Oh, okay. I see. Okay, yeah, it's 45. Away from the 45, it will be symmetric across, okay, and reduce in the length. So the result is here. Maybe I show you the result first. I have drawn here. Here is the result. So 45 degrees is the furthest. So if you pick any other different angle, either less than 45 or greater than 45, you will have the same. You will have a symmetry. Okay, you have a symmetry here. So away from 45. So this green here, right? So the bottom green is symmetric. You have the same distance with the angle that you throw at. Okay, so let me label some angle here, easier to say. Otherwise, too many. Let's label some angle here. So let's say the first green part here is alpha 1. Okay, the second here is alpha 2. And then let's call the first red one is beta 1. And then the second one is called beta 2. Okay, you can see that beta 2 and alpha 1 have the same endpoint. Okay, although you throw at different angle. And beta 1 and alpha 2 has the same endpoint, although they are different angle. Okay. And how I decide this? Okay, how do I decide this? This is decided from the sine curve. So this is decided from the sine curve in this computation here. You can go and read the computation. It's depending on the sine curve, because the sine curve. You know what's the sine curve? So sine curve is the greatest at the 45 degree, and then away from 45, you can see that it's symmetric. Okay, so this decides the symmetry here. So you don't think that I throw very high, you will go very far. It's not true. Okay, it's exactly the same as you throw at a smaller angle actually. So you get what I mean, or not? Sometimes you think you put a lot of effort, you get a lot of things. Actually, it's not true. Only you put in the right effort, then you get the most thing out. Because you'll see that, hey, why that people put less effort than me, also do the same. Okay? Proof here. You see, less effort, you also get the same point. Huh? More effort, you also get the same point. Only the right effort will get you the furthest point. You know, you need to use the right way. Okay, if you don't use the right way, you will cry as the red light. People just do the green light. Okay, no? Makes sense. Okay, you must use the right way. Right way is very important. That's why I like mathematics. Okay, you need to use the right way. Okay, no? Yeah, no time already on how to do exercise. Next time, I think there's few exercise we should do before we move on for the double integral stuff. Okay, maybe we'll do exercise next time, and then we will have to go into vector calculus next week. Okay, otherwise we don't have time. Okay. Okay, for those who have questions, you can say and then ask about your project. Okay. Okay. Any more questions about this chapter? Okay, so let's give a brief summary of this chapter, what you need to know. Okay. So if you do revision of this chapter, make sure you know how to go from parametric equation to curve back to parametric equation. Okay, you need to master this. How to do differentiation? You just do coordinate wise. How to do integration? Coordinate wise. How to do limit? Coordinate wise. Okay, that's all. Because you don't need to use definition, so you need to know how to compute only. And then about the tangent vector, very important. This is a very important concept in vector calculus later. How to get the tangent vector? You just differentiate your vector value function. And then how to get unique tangent vector? You need to just divide your vector by your length. This is just unique length vector, right? Okay. And then yeah, that's all what you need to learn from this chapter. And then next 2 weeks, be ready. We will put all the knowledge together. Integration, parametrization, everything. Okay. Yeah, we'll see you next. Or not next, tomorrow. tomorrow. And please come early to prepare. Don't come late. We want to start early finish.
我的那个大概是这样的，就是
有没有那种祈祷回去的？